Electrical conductivity in semiconductors. In semiconductors, the crystal lattice has a specific structure. For example, in silicon, each atom's nucleus forms a covalent bond with 4 neighboring nuclei, sharing 1 electron with each of them. As a result, freeing an electron from the valence shell of an atom requires much more energy compared to conductors. At room temperature, the band gap energy for silicon is about 1.1 electron volts, and for germanium, another semiconductor, it's about 0.67 electron volt. Recall that 1 electron volt is equivalent to 1.6 times 10 to the power of minus 19 joules of energy. Since the bandgap energy of semiconductors is much higher than that of conductors, we expect that at normal temperatures, far fewer free electrons will be liberated. Consequently, we expect semiconductors to have much lower conductivity than conductors. And indeed, this is exactly what we observe. Silicon has a conductivity on the order of 10 to the power of minus 4 Siemens per meter. Germanium has a conductivity of about 2 Siemens per meter. Conductors, such as copper, have conductivities on the order of 10 to the power of 7 Siemens per meter. In the crystal structure of semiconductors like silicon, where each atom forms covalent bonds with 4 neighboring atoms, it is still possible, even at ordinary temperatures, for an electron to break free and become a free electron. In this context, we can refer to the following definitions. An electron that remains bound to the nucleus and shared within the covalent bond shown here in blue. A free electron. An electron that has broken free from the bond shown here in yellow. A hole. The vacancy left behind by the freed electron, that is, a missing electron in a bond. This vacancy can be treated as an effective positive charge, since it represents the absence of an electron. It is shown here in purple. So, in semiconductors, every time an electron breaks free from the crystal structure and becomes a free electron, a hole, a vacancy where an electron is missing, is created. If we denote the density of free electrons as n, this must equal to the density of holes, denoted P. Since for every electron that is freed, exactly one hole is created. Therefore, in a pure semiconductor, under normal conditions, n equals to P equals to n sub I, where n sub I is called the intrinsic carrier density. So, in semiconductors, in addition to free electrons, which we denoted as n, we must also take into account the vacancies left by free electrons, or holes, which we denoted as P. Now, in a semiconductor crystal lattice such as silicon, neighboring electrons can move and fill adjacent holes, effectively creating a kind of hole movement within the lattice. However, the key point is that this hole movement, in the absence of an external field, is random and disorderly, just like the motion of free electrons in the absence of an external field. So if we assign a motion vector to each hole, for example, vector p sub I for hole number I, the sum of all these p sub I vectors in the absence of an applied external field is zero. This random hole movement, therefore, does not produce any net current. However, in the presence of an external electric field, the motion of holes must be examined. In this case, the external electric field causes neighboring electrons to gain energy in the direction opposite to the field. So the filling of holes by neighboring electrons is no longer random and disorderly. Instead, it appears the holes themselves are moving in the direction of the field. In reality, though, it is neighboring electrons moving opposite to the field that are filling the holes. Therefore, here the motion of holes is an ordered motion, and it results in a conductivity rising from holes, which we denote as sigma sub p. Following a derivation process similar to the one we used for conductivity in conductors, we arrive at sigma sub p equals to Pe mu sub p, where mu sub p is called the hole mobility. Now, let's also add the free electrons in semiconductors. They also move, but opposite to the direction of the field. So we also have a conductivity arising from the motion of free electrons, denoted sigma sub n, equals to ne mu sub e, where mu sub e is the electron mobility. So in semiconductors, two types of conductivity are defined, one arising from the motion of electrons and one arising from the motion of holes. The sum of these two conductivities constitutes the intrinsic conductivity of the semiconductor. In a pure semiconductor, N equals P equals N sub I, which is the intrinsic carrier density. So, substituting N and P into the equations for sigma sub N and sigma sub P with N sub I and factoring out N sub I E, we arrive at the following relation. Sigma equals N sub I E times mu sub E plus mu sub P.